Okay, well, good afternoon. Good to see you all. How many of you have been down to the Ark already? Been down the Ark? A few, okay. How many going tomorrow, going down the Ark? Okay, that's about everybody else. That's great. And we went there yesterday, and you go look up at that Ark, you say, well, now I know how they got all the animals on the Ark. Well, you heard I was the Bob Jones University Science Ambassador after teaching at Bob Jones for 39 years. And you may wonder what a science ambassador does, but we travel around the country and try to introduce people to the wonderful science and engineering programs at Bob Jones University. And I know that sometimes people have to leave early because they have another appointment or at the planetarium or something. So if you are in grades 7 through 12, we have some cards on the table. If you could just fill one of those out before you leave and put it in the box, we'll enter you into a gift card drawing. Just wanted to mention that. Okay, our topic today is the mysterious electron. Electrons play an essential role in a number of physical phenomena. Of course, you're familiar with energy generation and electricity and so forth. And magnetism has to do with electrons. We'll talk about that more later. One you may not have thought about is thermal conductivity, the fact that heat is transferred by electrons. And then, of course, chemistry. I'm a chemist, and so chemistry has a lot to do with moving electrons around. If you understand how the electrons move, you can understand a lot about chemistry. So just to start off with that, let's look at electrolysis of water. We would call this a combustion reaction when we recombine the oxygen and the hydrogen. But what we're doing here is we're actually tearing the water molecules apart. Jacob, you want to come up here and help me out with this? So what I have here is a couple of platinum electrodes immersed in sodium sulfate. And I'm using those electrodes to rip the molecule apart. I'm tearing electrons off the oxygens and putting them on the hydrogens and getting hydrogen and oxygen gas. Did you get your
safety goggles on?
Safety goggles, good. So see what I have here, Jacob, is I have some hydrogen and oxygen bubbles, just little bubbles here. And what I'd like you to do is to get them over their activation energy barrier and recombine them into water. Okay. Just touch the splint to the bubbles then. Thank you very much. So you heard the loud bang there. Just a little froth of bubbles there, hydrogen and oxygen. Sometimes we talk about using hydrogen for cars. And I was thinking about that. What if you have two hydrogen cars, striking each other, having an accident? Well, you probably wouldn't need any lawyers, okay? Because there wouldn't be anybody left to sue. There'd just be a big crater in the road. So a little bit of hydrogen and oxygen go a long way as far as explosions are concerned. Thermal conductivity is based on electrons as well. Who are we going to have to help us with that?
We're going to have Lydia come up.
Lydia's going to come up with that? Okay. So I have two blocks here. Do you want to come up here, Lydia? Thank you. And they look very similar to each other, but Lydia's going to tell us how they feel. So hold this one in this hand, your left hand, and hold this in your right hand. Now tell me how they feel different, how they differ from each other.
This one's lighter and this one's heavier.
Okay, so it's lighter and heavier. Is there a temperature difference? Does one feel colder than the other?
Yes, this one's colder and this one's warmer.
So this is colder and this one's warmer, okay? So we'll put these here, Lydia. Now what we're going to do is we're going to put an ice cube on these. Now which one do you think will melt the ice cube faster? The colder, heavier one or the lighter, warmer one? Okay, so let's see if that's true.
You didn't take a vote out there.
How many think
the colder one? How many think the colder one's going to? Okay, how many think the warmer one's going to?
Okay.
Okay,
So now we'll put the two ice cubes on here. Now you watch. What's happening there? Can you tell the audience what's going on?
This one is melting quicker on the colder one, and this one's melting slower on the warmer one.
Yeah, so almost immediately you can see the colder, heavier one is actually melting faster. You can go back, have a seat. Thank you. So why is that? Well, the colder, heavier one is just a block of aluminum that's painted black. And it has a sea of electrons. Metals have seas of electrons. Electrons are free to move. That's why they conduct electricity well, but it's also why they conduct heat well. And so you can see that it's not going to take long before this one on the aluminum block has become a puddle. And the reason why Lydia thought that the one was colder, they actually were the same temperature. But the reason you thought they were colder, it was colder because it conducted the heat away from your fingers, and your brain interpreted that as being colder as it conducted the heat away from your tips of your fingers. And so that tells you about the sea of electrons. It not only gives electrical conductivity, but thermal conductivity as well. You can see this one's hasn't hardly melted at all, and this one's going to be melted completely in just a little bit. Are there electrons in the Bible? Well, there certainly are. Here, the children of Israel traveled to Sinai, and they're looking at the mountain, and it said all the people saw the thunderings and the lightnings and the noise of the trumpet and the mountain smoking, and when the people saw it, they removed and stood afar off. And we know that volcanoes can cause lightning. The dust grains rub against each other, and there's a charge accumulates in one place in the cloud, not in the other, and then we have lightning to try to neutralize the charge. And so they're afraid of that, and maybe they're right to be afraid. Now, when I was 12 years old in New Jersey, I grew up in South Jersey, and we used to go huckleberry picking. How many of you people have ever been huckleberry picking? Anybody been huckleberry? I ever get a few there. Some places I go, they don't even know what a huckleberry is. It's a wild blueberry, and we were out in the sandy area there in South Jersey picking huckleberries, and a thunderstorm came up, kind of like the one we had this morning. And it was scary. I was running to the car, and I'm up to my ankles in water, and suddenly the hair on my head started to rise. And you can see it kept rising. It went to heaven. My hair went to heaven before me. And
Hair? You used to have hair?
now I have a picture. By the way, this is my wife of 46 years. And I did have hair when we first met, okay? No matter what she says, I have pictures proof. I had a wave right here. I had a wave of blonde hair. It was just waving goodbye. Okay. So I was running for the car, and I felt the hair on my head stand up, and then a lightning bolt struck the tree right in front of me. And I felt the surge of electricity. Some people say that accounts for my personality. I'm not sure if that's true or not. But it can be scary. Now, here's some reindeer that didn't do so well. 323 reindeer were struck dead by a single bolt of lightning. Now, reindeer have a problem. They have front hooves and back hooves, and so there can be a potential difference between their front hooves and back hooves. And so when you're out in the lightning storm, kids, what you want to do is you want to put your feet together.
Your hooves together.
Your hooves?
Your legs together.
Kids don't have hooves.
I know.
Okay, here we go. And then just crouch down like this. Try to get as low as you can. Now, what did they tell you when you were a kid?
They told me to get as flat to the ground as possible, like in laying flat on the ground, which is the worst thing to do.
Right, because the electricity can go right through you.
Yep.
Yeah, now, of course, that's back when they didn't like kids.
I mean, after all our playgrounds were concrete and metal.
Yeah,
right?
we had no soft surfaces at all. And our parents would send us out to play, and they would just say, come back when the street lights come on. Nobody cared where we were. They probably had a sign on my back that said, take this one, but nobody ever did. And some of the older folks may remember that. We used to have in the shoe stores, we had x-ray machines where you could x-ray your own feet. Do you remember, some of you remember that? And Thomas Edison actually invented it. It's up in his museum in East Orange, New Jersey. And we'd run in as kids, we'd stick our feet in and look at the bones in our toes. So I lived during a time when they let children x-ray their own feet. We don't do that anymore.
And we actually went to Edison's museum 2 years ago, and he was telling the guard this story, and he looks down at his feet like, are your feet okay?
He looked at me like they're going to fall
Says,
off.
that's dangerous. It is dangerous.
Yeah.
Can you see I'm going to take this away now,
Okay.
but can you see how?
Yeah.
That one's
Yep.
done.
So as far as lightning is concerned, I think lightning, every 600,000 lightning strikes, one person is struck. But the interesting thing is that only 30% of people that are struck by lightning are killed by it. And I'm going to tell you the reason right now. So I have an Odin coil here. And this Odin coil will take the house voltage and transform it to 50,000 volts. And I'll hold on to this, okay?
Oh, I have the rail.
That's all right. This is fine. This will
Okay.
work. This will
Who are you
work.
going to touch?
Hmm?
Who are you
It's
going
good to- it's good to touch you. Okay, so you can turn the lights down.
Did you already ask them why he's
No,
not going to drop dead? Okay, he's going to touch this, 50,000 volts. So the question is, why doesn't he drop over dead?
Do you know where my life insurance is? There's always the first time.
Maybe
Okay,
I
here we
better.
go.
Okay, if it's the first time, it's also the last time.
That's right.
Okay, here we go. 1, 2, 3.
And it's all on TV.
Did that mess your cameras up?
Didn't seem to.
Sometimes it does.
Okay.
Good, okay. You can become a human light bulb too.
Okay, so why didn't it kill me? What do you think? Because I'm holding metal?
Yeah.
No, don't do that.
Yeah,
Don't do that's a bad idea when
He
you're in a
thinks
golf
you're-
course.
He thinks you're holding metal.
Let's try it without the metal. See how it works.
No, you have to put your,
Oh yeah, I better do that. Well, I was just going to do.
yeah, but we have to show him
Okay.
why you didn't drop dead.
Okay, here we go. Okay, I'm still alive. Okay, what do you think?
Because you're grounded in some way. I don't know how, but
I'm not grounded. Okay, so the reason is because electrons have a negative charge and like charges repel each other. And so they're trying to get away from each other. They're trying to get on the outside of my body rather than on the inside. Okay, and that's what saves me. That's the reason why only 30% of people struck by lightning are killed by it, because even that terrific amount of lightning, we're talking about, you know, 1 billion volts and 50,000 degrees Fahrenheit and so forth, it tries to flow on the outside. Now, sometimes you're reading the paper, some golfer's out there with his golf club and so forth, and he gets hit, and he survives, but all his clothes are burned off, and that's the reason why, because it tries to go on the outside of the body. Back when I was young, they used to try to execute people with an electric chair, and it didn't work very well, and the Supreme Court actually said it was cruel and unusual punishment because electrons don't want to go in, they try to go out, they try to repel each other, so it was very hard to kill somebody with an electric chair back in those days. Okay, I have, this is a new one we've been working on, and sometimes it works and sometimes it doesn't, so I'm going to put some
You always say that the people remember what didn't work
That's right.
more than what did work. Right?
Right, so I'm going to put some ethanol in here. And the idea is, now, when Jacob was up here, he had a splint, and he touched it to those hydrogen-oxygen bubbles. He raised it up over the activation energy barrier and allowed them to combine into water. In this case, I'm going to do combustion again, but this case, I'm going to try to use the Odin coil to try to make it go. So we'll see.
Are you going to try to do them both at the same
I'm going
time?
to try, yeah. I put the two bottles here. I'm going to see if we can do it at the same time. So I'm going to use a spark to try to get it over the activation energy barrier. See how we do. That one decided not to work. See, now you remember it better. Because it did work.
The first one was good.
Okay.
Oh, it's down there.
It's all right. We can get it later.
Okay.
All right. I don't know why that one didn't work, but I'll take another look at it.
Is it okay if I take the lid off?
Sure, go ahead.
Okay.
Yep.
Make sure.
It won't
You
hurt you.
never know.
Won't hurt you. Here you go. Here's the other one.
Thank you.
I'll work on that one.
Okay.
Always do two, and that way one at least works. Okay. How many of you have ever heard of the word fulgurite? Heard that? Okay, fulgurite. Anybody else? Smart kids down here got fulgurite. Okay. So the fact that you haven't heard about fulgurites is actually a proof that the Earth is young. Let me explain that to you. So a fulgurite is just fossilized lightning strike. So when lightning strikes sandy soil, it forms something like that, glassified sand. Okay? And then you see the beach erodes away, and you can see it and so forth. You can buy pieces of them on eBay if you want. And there was a couple scientists who were down in Tampa, Florida area, and it's very sandy soil. They get lots of lightning there. And they were trying to figure out how often lightning strikes the ground and around the world at any particular time and so forth. And so they looked at how many times a fulgurite should form over a 4 billion year period, if they thought the Earth was 4 billion years old. And so they decided there should be about 4,000 fulgurites per square meter, okay, because of how many lightning strikes there'd be over that period of time. So if the Earth was old, it was billions of years old, everybody in this room would know about fulgurites, because every time you tried to plant a garden, you go clank, clank, you'd hit it, right? So the fact that only very few of you know about fulgurites is evidence of the young age of the Earth, okay? So that's evidence of God's creation not too long ago. Okay. Well, I talked about the mysterious electron. Let me tell you why it's mysterious. So first reason it's mysterious is because of wave-particle duality. J.J. Thomson won the Nobel Prize for describing the electron as a particle. You know what a particle is? It's like a baseball. You can throw it, it bounces off things. It has a particular point in the space where it is, okay? And his son, George Thomson, won the Nobel Prize for describing the wave-like properties of an electron. And waves are different. I mean, there's lots of waves in this room. There's radio waves and light waves and sound waves and so forth. You can't say, well, it's there and it's not over there. It doesn't have a particular position. So what is it? Is an electron a wave or a particle? And the answer is yes, it is. And now we should be able to handle that idea because as Christians, we know that Jesus Christ had a dual nature. Okay? So is Jesus Christ, is he man or is he God? And the answer is yes, he's both. Okay, all man and all God. So we understand about duality. Duality nature, duality in reality. What else is mysterious about electrons? Electron spin. Now, every chemistry course taught in the world, in the first course, they're going to teach students about electron spin. As electrons move through a magnetic field, they act as though they are spinning, okay? But nobody actually believes that they're spinning, okay? And even if they were spinning, we couldn't tell it. You know, the electron's the roundest thing. If you think of it as a particle, it's the roundest thing in the world. They said that if an electron was the size of the Earth, if you took 2 nanometers off the South Pole and put it on the North Pole, that's how round it is, exceedingly. So being perfectly round, you wouldn't be able to tell it was spinning, okay? And so nobody actually believes it's spinning. But we talk about it like it is. And this is a good example of the fact that science can only deal with models. It can't deal with reality. And as scientists, we're used to that. We're used to dealing with models. We understand that that's not the reality of the thing. The reality is a lot more complicated. In many cases, things we don't understand. This idea about the electron being mysterious, electron spin, is something I can't explain to you. In other words, what we would say in science, there's no classical analog. There's nothing I can say it's like this, because there is nothing else like this that I can explain it. And so we just go on our merry way talking about electrons having spin, even though we don't know that they don't actually spin. That's pretty mysterious. What else do we know about electrons that's mysterious? Electron charge. Now here's a definition. Electric charge is a physical property of matter that causes it to experience a force when placed in an electromagnetic field. Well, that's true, but that doesn't tell us what charge is. It tells us what charge does in an electric field. Now, if you know what charge is, don't tell anybody, just tell me afterwards, and we'll both get the Nobel Prize, because nobody knows what charge is. Okay? Richard Feynman, one of the greatest physicists in the 20th century, said, no one understands charge. And it says there are two types of electric charge, positive and negative. Well, that's true. So, but why aren't there three types of charge? You know, why not positive, negative, and purple or something? Why not 5 types of charge? Why only 2 types? No one has an answer. And like charges repel and unlike charges attract. Again, why? Okay, that's what they do. And so another reason why science makes a very poor religion. The religion of science we call scientism, the worship of science. You know how theologians are able to exactly define their terms. Okay, and they may not agree with each other, but they can exactly define the terms that they use. But scientists, we often have to deal with things that we can't really define, and that's like electric charge. That's why science, again, makes a very poor substitute religion. Well, when I talk about these things, I like to talk about the pioneers of science, Christian men of science, because a lot of times when I talk to teenagers in high school, I'll say, who was a pioneer of science, a Christian pioneer of science that you can remember? And they'll look at me, you know, and they'll say, Ken Ham? So, well, not Ken Ham. He's a little too young, all right? So somebody a little older than that. And so I like to introduce them because I'm afraid they think that science was somehow invented by atheists or agnostics. But we have a wonderful Christian heritage in science. Now I want to introduce you to Michael Faraday. Michael Faraday is the ultimate rags to riches story. Grew up in a very poor home. His father was a blacksmith and was disabled. And so Michael had to go work at a young age and support the family. He became an apprentice to a bookbinder. And he was so sorry he couldn't get a formal education that he used to meet with other young men. They called themselves the mechanics. They would meet together in the evening with candlelight and try to practice pronouncing words and spelling words and their penmanship. And one of the things they could do to improve themselves was go to the public lectures at the Royal Society. So Michael Faraday attended, and the man who gave the lectures was the preeminent scientist of the day. That was Sir Humphrey Davy. And Michael Faraday wrote down everything he said in his beautiful penmanship, bound it into a book, and presented it to Humphrey Davy. And Humphrey Davy was so taken by this that he hired Michael Faraday to be his janitor, to sweep up and to wash the glassware and that type of thing. And Michael Faraday went on to become the leading scientist of Great Britain at the time, taking Humphrey Davy's place. Humphrey Davy wasn't especially happy about this either. But amazing, Michael Faraday loved God. He saw in nature the unity that God had created, and that helped him with the discoveries that he made. He was a member of the Sandemanian Church, an offshoot of Church of Scotland. They were very strict, and they didn't believe it was proper for any Christian to accept worldly honors. And so here he is, the most famous scientist of the day, and he wouldn't accept any honors that they tried to give to him. Now, Queen Victoria said, well, at least you can have lunch with me. He said, yeah, I can have lunch with. So he had lunch with the Queen, and he missed one of the Sandemanian meetings, so they excommunicated him. And so they were a tough bunch. But Michael Faraday loved God, and he's one who helped make the electron less mysterious than it is. Now, Michael Faraday didn't have a formal education. He didn't have the mathematical background, so the Lord led this man, James Clerk Maxwell. He came from a different part of society. He was upper middle class. And no other than Einstein said that James Clerk Maxwell was the finest mathematician of all time. Okay? Terrific mathematician. And James Clerk Maxwell loved God as well. In fact, he wrote a song. He wrote a hymn for his students to sing about the Creator. Don't worry, I'm not going to sing it for you, okay? Especially since we're on TV, okay? But he wrote that song to honor the Creator. Unfortunately, James Clerk Maxwell died at a young age in his 40s of colon cancer, died an excruciatingly painful death. But he said to his pastor, he said, "I've tried all the world's philosophies and found them wanting. The only thing that satisfies is Christ Jesus, my Savior." And he was a great man and a godly man. And from him, we got what we call the Maxwell relations that actually took what Michael Faraday had discovered and actually put them in mathematical form. So what do we know about electrons? We know that they're very small.
You see the electron is at the end of that arrow. You see where the arrow goes? That's how big the little electron is.
Okay, turn the lights down a little bit. Okay. So we've been married for 46 years, but there's still electricity in our marriage. Okay, so just get some out of your nose.
Is it going to hurt? Oh.
Let's see if there's anything up there. Not much.
Do you want to see my favorite one, though? Okay, it's going to be fast. Now, can we have the children on the front row come on up here for us? What we like to do is see how many people we can get this electricity to go through.
Here, I'll take this to...
Okay, so we all have to hold hands in a circle. Can you all see us all right? Come on up closer up to the stage here. And
Okay, so how are we going to do this? So why don't you, let's see, I'll hold your hand, and you hold Mrs. Matsko's hand.
you want me
There.
to come over here?
Yeah, you come over here.
Sorry.
And then I'll put this down, because I don't think we need it. And then
Okay,
we'll
you ready?
Hold it like this.
See if you feel anything. Okay, you let me know.
Now somebody let go of their hand. See?
When we do this in a classroom, you
Now
can
if
tell
we could have
when someone lets go of their hand.
see, you can go through metal like that.
Okay, let's try 2 of them. Here, you hold this,
Okay.
and you can, how about you and Lydia? No, that won't work.
Here, you put your fingers in the,
You put your finger in there. No, we have to have, that doesn't work.
you had to put your finger in. You're having a hard time with this, aren't you?
I know, I can't put okay, we'll put it here.
There you
Both
go.
of us put our fingers in it. Okay,
There
there
you
we go.
Okay.
Good, good job. Okay.
Thank you.
Thank you very much.
Yep, they did a good job. So I don't know how much current was flowing through at just that time, but less than a milliamp, that would be less than anybody could feel. Nobody felt anything. So 1 milliamp, that's 6.25 times 10 to the 15th electrons per second flowing. Okay, 15 zeros after it per second. Okay, gives you an idea how small electrons really are. Very, very small. Now, what else do we know about electrons? We know that they can influence things around them. So I have a plasma ball here. Probably going to need the lights down again. Okay. And here's my energy tube, and I can bring it in. And notice the red turns on first. Well, they're all kind of turning on at the same time. See if I can get further away.
I can't really see it up there.
So red goes first, and then the green goes on, and then the blue goes on way out here. So Michael Faraday, he would have thought of this as a field of electrons coming out from the ball, turning those on. Okay, and we can break that circuit. We can block that field with a piece of aluminum like that. See, just like that. Okay. What else do we know about electrons? We know they're induced to flow by magnets. We have the lights again. You
have your hand crank generator?
Yep. So one of the things Michael Faraday invented was the electric generator. So my little hand crank generator. So I ate my Wheaties this morning. And so my chemical energy is going to be turned into mechanical energy. And then there's a little magnet in here, and it'll spin through a coil of wire. and then that'll light the light bulb. So all according to the first law of thermodynamics. Now the opposite of you have my, you're going to hold this for me?
That's right.
Okay, so here's a motor, and a motor is just the opposite of a generator. In this case, the electricity goes through the coil of wire and causes the magnet to move, and so I can cause it to go this way or this way. Okay, and so motor is just the opposite. Now think about how much in our society is based on motors and generators. Now, Michael Faraday didn't want any honors. He refused honors, but he got one anyway after he died. This is a capacitor, and we measure capacitance in farads, okay, for Michael Faraday. So he got one after all. This is a 1 farad capacitor, which is extremely large. A 1 farad capacitor when I was these kids' age would have been the size of a filing cabinet. But we make them a lot smaller these days. So I'm just going to try to turn the generator into a motor. Capacitors hold their charge by, you have like a plate with positive charges and a plate with negative charges, and because they attract each other, they're held in place. So you can hold energy in place and collect the electrons in a capacitor. So I'm going to put this, we're going to see if we can charge it up.
You ate your Wheaties?
I ate my Wheaties.
You didn't have Wheaties.
Didn't have
What
Wheaties?
did you have for breakfast?
Oh, it was wheat checks, I think. Okay, here we go.
That gives them lots of energy. Come on, more and more.
Okay, unhook it. One
Okay,
of
here we
them.
go.
Okay, now put it back again. Notice that the electricity goes back in and turns the generator into a motor again. Okay, from the capacitor. Now, James Clerk Maxwell, he was able to apply his mathematical knowledge to this phenomena, and he came up with Maxwell's equations, which describe magnetism and electricity. And, you know, it's interesting, by the way, that mathematics should so describe the natural world so well. Did you ever think about that? You know, why should you have to study mathematics to become a scientist? Well, the secular scientists have no answer. I saw a Nova special where they spent 50 minutes trying to figure out why math describes the natural world. It describes the motion of planets and the growth of a leaf and photosynthetic process. There's no reason for this unless the same God who created the natural world also created mathematics as well. We understand it, something that others don't understand. Well, this is a ring launcher. I bet you can figure out what a ring launcher does. It launches rings. Very good. And usually somebody will say, does it do anything else? And the answer is no. It's a complete loss as far as doing anything else. But it's good for illustration purposes. So we have...
Let me see. Okay.
Okay, she's afraid I'm going to break one of the lights. Okay, so we have the electricity going this way around this coil. That produces a magnetic field according to the right-hand rule. Electrons follow the right-hand rule. You say, why don't they follow the left-hand rule? I don't know. God made them that way, right-hand rule, all right? So North Pole this way, and then we have that induced magnetic field will produce a magnetic field around, electric field around the coil here. That produces a magnetic field this way. So you have two North Poles facing each other, and that's why the ring flies up in the air. So let's see. Okay. I'll do it one more time so you can see. We get the kids up here so they can feel the magnet.
You 5 kids want to come back up again?
While they're coming up, let me show you that we can actually convert it to light, so we can have electricity go through the coil of wire, and we can light the light bulb. Or you can see the magnetic field here with these little toy magnets. You can see them spin.
Come on up.
See how they spin like that? It's a magnetic field that's
Put
produced.
your hand around this, okay? Just
The kids come here and hold the magnet near the coil so they can feel the magnetic field.
Just hold your hands like that. Can you reach?
Okay.
See if they can feel it.
Okay. I think they felt it.
Okay.
What do you think? Okay.
Thank you.
Want to feel it one more time?
Do they want to feel it one more time? Okay, and then we'll have you 2 guys try it.
Okay. See? Okay. Hand it to the other guys. Thanks for your help.
Thank you. Just put them right up there.
Yeah, you can feel the magnetic field.
Thank
You know, when they show you lightning on the weather forecast, you know, they show where the lightning is and so forth. You know, what they're looking at is not the electric field. They're looking at the magnetic field. The magnetic field can travel hundreds of miles, and so that's what they're picking up when they show you where the lightning strikes are. Anyway, I thought you'd enjoy that. So this goes according to Lenz's law. Lenz's law, when you push a magnet into a coil of wire, it resists your action. When you pull it out, it resists you as well. And so it acts kind of like a magnetic braking system. So I have this rail here. Thank you, hon. And now aluminum rails are not magnetic. This is a magnet, but you can see that it's not magnetic at all here. But I can induce an electric field to flow through the rail. So let me roll this down. This is just a marble, so you can see how long it takes. It takes about 1 second, 1001, okay? Now I'll put the magnet here, and as the magnet moves, it produces an electric field that opposes the magnetic field, and it'll break the magnetic marble. It'll go down slower. 1001, 1002, 1003, 1004, 1005, 1006, 1008, 1009, 1010, 1011, 1012, okay?
Now, some of them may have been in an amusement park where you have one of those free fall drops, you know, rides where you just get dropped really fast.
What you're paying for is not the drop. That's free. What you're paying for is the mechanism at the bottom to keep you alive. Okay? What the amusement park people are afraid of, they're afraid that when you're halfway down, the power is going to go off in the park, and you're all going to die at the bottom. And that's bad for business. Okay? And so they have these big copper plates and big magnets to this passive braking system to keep you alive at the bottom. So now you know you don't have to be afraid. So you can see if I put a marble in here, it goes right through, just like that. If I put the marble in here,
No, the magnet.
the magnet in here, look how long it takes. See, it goes very, very slow, okay, because of that magnetic braking. They also use magnetic brakes on like city buses to recapture some of the energy. Okay, so that's Lenz's law. What else do we know about electrons? We know that they're exchanged during redox reactions. Now that combustion reaction, that was a redox reaction. I'm going to do another redox reaction now. And I'm going to use hydrogen peroxide. This is 30% hydrogen peroxide. And this is called the catalytic decomposition of hydrogen peroxide.
Yeah, it's not the same kind of peroxide you have at home, so guys, don't try this at home, okay?
Okay. Then I'm going to put some soap bubbles in here so you can see the oxygen form. You can see on the slide, you can see that we add a catalyst. So this activation energy barrier we have to get over. And so we add a catalyst that lowers the activation energy and allows it to take place at room temperature. You have catalysts in your body called enzymes that help you digest your food so you don't have to be a big fireball after lunch. Okay, so here we go. We're going to put the catalyst potassium iodide in here.
Just a minute.
What's wrong?
I just want to pull this back.
Oh, she's afraid I'm going to make a mess, which I often do. Okay, here we go.
Yay, it all stayed on the cloth.
See,
Sometimes it goes
all
over.
your fears were unfounded. And you can see the heat that's coming off as well. So there's electrons being exchanged here. You can't see them because they're too small, but they're actually being exchanged and releasing all the oxygen that we have there.
Hey, what do we call it sometimes?
Sometimes they call this elephant's toothpaste. Okay? Yeah, I think, is it Miss America did elephant's toothpaste, I think, when she won her competition? Okay. I guess I could win that competition. No, I guess I could. All right.
Whoa.
What else do we know about electrons? We know that electrons are exchanged. When electrons are exchanged, metals can be reduced. Okay, so I've been soaking some pennies in sodium hydroxide and zinc. How many pennies do we need? Okay. So, and this is an old alchemist trick. Back before there was chemistry, there was alchemists that used to go from one place to another. They say, "Oh, king, live forever. I'll turn all your copper into gold." And the king thought that was a pretty good deal. And the idea was to turn it into something that looked like gold and get out of town before he found out it wasn't really gold. And so what he'd do is he'd soak the copper, like I did, in sodium hydroxide lye, and then he would heat it. So you can see it looks silvery. So silver is kind of the next step, right? And so then I'm going to heat it. And so zinc combines with copper to form brass. And we'll show them what that looks like.
I don't know if you can see that or not.
Looks nice.
So ladies, wouldn't you love to have a husband who could turn pennies into gold? Unfortunately, it's still only worth a penny. Here, we'll give one to each family for volunteering.
There you go. So there was an alchemist that went to the court of the Chinese emperor, according to legend, and he said, "I'll help you live forever." And what he did is he took egg yolk and mixed it in with mercury, liquid mercury, and had him drink it. Looked like liquid gold, right? And of course, mercury is very toxic, and so it killed the emperor dead as a doornail. But the emperor's body had so much mercury in it that it killed a lot of the bacteria that would normally cause them to decompose. So they thought they were on the right track after all. It's interesting that alchemy got its start. They weren't so much interested in the gold as money as they thought it had the essence of eternal life. Okay? Because you could take a gold bar. I think just last year we found some gold coins they dug up in Jerusalem that were there from the fall of Jerusalem, 70 AD, and you dig them up and they're still bright and shiny gold. So they thought that gold had the essence of eternal life. So it's interesting, chemistry got its start with people looking for eternal life. And yet we know where eternal life is found. It's found in Jesus Christ, God's Son, who died on the cross for us. What else do we know about electrons? We know they produce a lot of heat when they're exchanged. So I have I'd like to do this thermite reaction for you. If I did the one on the left-hand side there, we'd have to evacuate the building. So that doesn't work. Actually, I had a colleague who did it at Bob Jones, and we had the fire company come, and it was pretty exciting. But what I'm going to do is I'm going to wrap some aluminum foil around this rusty ball, and if I hit it just right, if I can hit a piece of rust with the aluminum, I can get some electrons to come out and some heat. See if I can. Oh, there's one. Maybe turn the lights down. Maybe you can see if it's even better. You see that? Yeah, that was a good one. Okay. So that's the thermite reaction, a little safer way of doing it. It actually burnt holes in the aluminum foil there. They use the thermite reaction to actually weld railroad rails together, so you don't get the clickety-clack. Okay, and then they take balls like this and they use it to smooth the rails out, so you can't feel the joint. Okay, so you might see balls like that laying along the railroad track sometimes. But you can see all the heat that's given off when those electrons are exchanged. What else do we know about electrons? They can be pushed around by light or heat. So this is a spiroxene, and so you can see where it comes apart there. That's actually, there's 4 bonds there. Those of you who know something about chemistry, that's sp3 hybridized, so it's tetrahedral, okay, like this. And then we shine UV light on it, breaks one of the bonds. The molecule twists like this, and it can pick up the conjugation on either side and absorb visible light. So we have some beads here, and they have some of that spiroxenes in there, and so I'm going to shine the UV flashlight on them and reveal the hidden message,
That's so cool.
which is BJU. Okay.
Come to Bob Jones University.
Right. Okay. So we taken that technology and we've actually put it into transition lenses. Okay, so here's some transition lenses.
I think it needs to be better.
You'd never know she was a perfectionist, would you? All right, and so shine my ultraviolet flashlight one side here, and notice it turns dark. So we use it for transition lenses to make it dark.
And then we were staying with the optometrist last fall and found out that they now make transition contact lenses as well.
And it turns really fast. Doesn't take long at all to turn. And the reason it's so fast is because the molecule twists like that. If you embed it in hard plastic, it goes slower, and soft plastic goes faster because it's a mechanical effect. I asked my colleague, Rick Mowry at Bob Jones University he teaches our molecular modeling course. I asked him to model it on his computer. So there it is, the red balls where it breaks apart. You can see it's only absorbing the ultraviolet light. And then when it breaks apart, you can see it absorbs in the visible. We can make different colors by changing the substituents on the molecule. That's pretty cool, I thought. The Bible says in Romans 1:20 that the invisible things from the creation of the world, are clearly seen, being understood by the things that are made, even his eternal power and Godhead. So they are without excuse. I think I lost that. There we go. So important for us to